All right, so if you look, here are my imaginary flipping of a coin. So I have 30 imaginary flips, and it's such a strange happenstance that all of these ended up being heads. Did anybody else have that? What I want us to think about is we have an understanding of what this coin is supposed to be. This is possible, but pretty unlikely in this many imaginary flips. So it's possible, but not probable. And so if you count, how many times did you land on heads? Okay, so I had all 30, and I had tails, 0. Okay, even as you're doing an imaginary coin flip, you're probably going, oh, it's been a little bit since I've had tails, so I'll do tails. Oh, blah, blah, blah. Not blah, 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 but you know what I mean, where it's like, you probably talk yourself into switching at some point, even though it's possible that it's heads, and then heads, and then heads, and that you might have several in a row, and that's okay. And it's more likely than all 30, but still, we have an idea of what a coin should be doing. So did any of you end up with 15 and 15? Because almost all of us will probably be close to that, which is kind of funny that we didn't tell you that you had to do that, but we have an understanding of the probability of flipping a coin. So to simulate this a little bit differently, here's line 108 on table B. So this is from the front of our packet. And let's simulate tossing a fair coin 10 times here. We're going to record heads for an odd number and record tails for an even number. All right, so we come to 6, and that's going to be heads. So we're going to say even is heads, odds is tail. Okay, so 6 is going to be heads, 0 we would probably skip, but most people would consider that even, so I'm going to skip it. 9, we're going to say tails. 4, we're going to get heads. 0, we're going to skip. 7, we're going to get tails. 2, we're going to get heads. 0, we're going to skip. 2, we'd get heads. 4, we'd get heads. 1, we'd get tails. 7, we'd get tails. And the 8, we would get heads. So if I got 0, I skipped it. So most people consider that to be an even number, but sometimes it's just the absence of value. All right, so here's now maybe what we might consider a more random, because I definitely influenced my imaginary coin here. This would be more random here. So if I looked at this piece, so we have now our 8 times here, or 10 times, and I looked at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times here, which one's more likely? So we can start talking about the randomness idea. Okay, when we have a random 10 groupings, I mean, having 10 in a row is not probable, but it's possible. And so neither one of these would be a different probability there. Each one of those coins is independent. So getting heads on the first one, getting tails on the second one. Again, this coin isn't whispering like, you haven't had tails in a while. It doesn't know. Each one of those flips is going to be more, should be independent of the last one. And so on here, even though it seems more random to us, each one has the same opportunity of being heads or tails, even or odd. And just like this one, I might have influenced it a little bit, but if I really was picturing a coin, it would just be heads or tails each time. So which one is more random, imagined or simulation? They should be the same. Just like in this one, which of the following outcomes is more probable? Well, I have 1, 2, 3, 4, 5, 6 outcomes here, and 1, 2, 3, 4, 5, 6 outcomes here. They're still equally as likely. Just like this one, which situation is more random? I mean, I could say that I might have influenced the first one, but as far as randomness, they're both random. They're both equally as likely to happen because each one of those flips is a 50-50 chance according to probability. So here's an applet that you can look into more on that idea and kind of the randomness here, but there are some myths we want to address. First was the myth that is the law of averages, that you're due for something just because you've had a streak of one outcome or the other. And so one of the myths about randomness is that we are often tempted to look for or create a pattern. So frequently we are tempted to look for or create a pattern or explanation other than chance variation. If we see something that jumps out to us as a pattern, we start to see that as not random. But patterns could be random as well. They just are visually appealing to us. When I was in high school, my sisters got to go on the band trip with the band, or down to Florida. So it was the parade trip down in Disney. And so my mom was like, you don't get to go because you're not in band, but you get to paint your room whatever you want. So I painted my room bright yellow. It was awful. And I colored in blue and orange polka dots with like a sponge, like circle. And I tried not to make it a pattern or a design. I just wanted it to be randomness and different sizes of those two colors all over the bright yellow. When I stepped back, it was like in perfect diagonals. So even though I had attempted randomness, our brain tries to create patterns, okay? We don't like randomness. It's typically uncomfortable to humans. We want to always explain what's going on because randomness can almost feel chaotic in our brains. So one of the myths that we're seeing sometimes is that if we see a pattern, we say that it's not random. It's okay to have a pattern and still have some randomness there. Another myth is that a pattern doesn't equal not random. Okay, so this is still going back with that idea. It's not always the case. Our pattern doesn't have to equal not random. It can still be random within that same kind of variation there. So kind of keep that in mind. The other myth we said was the law of averages. Again, you're not owed a outcome. And so, for example, when we're starting to interpret probabilities, it says Pedro drives the same route to work on Monday through Friday. His route includes one traffic light. According to the local traffic department, there is a 55% probability that the light will be red when Pedro reaches the light. Interpret that probability. And so the way that we interpret probabilities is we would say based on many trials. And so probabilities are that long-term idea. So based on many trials before, there is a 55% chance from a long series of repetitions that Pedro will stop at the light. I guess that light in particular. And so this is a long-term probability. It's because he's done this for so long. It's because the local traffic department has lots of data on this. So even though he might get stopped 4 days in a row, it doesn't mean that the probability is off. That pattern doesn't equal not random. And so the probability here of 55% is because maybe in his long time of this, or the local traffic department kind of knows the times where it's going to be red and green if it's not triggered by something, this would be that 55% chance. And so, that would be frustrating to me to be like, oh my gosh, so more than half the time I'm going to get stopped at this red light, but that's just what happens. Okay, a couple more things looking at our probability idea. When we say that probabilities range from 0 to 1, they have this idea of how likely an outcome is to occur. So if we want to match one of the probabilities that follow with each statement, and then we can explain your answers to our neighbor, but it's more, we'll just kind of explain them in here. So it says this outcome is impossible. It can never occur. All right, so that would be 0. That means it's not going to happen. There's a 0% chance of that. Where this outcome is certain, it will occur on every trial. That would be 1, where it's guaranteed to happen. It's a 100% chance there. This outcome is very unlikely, but it will occur once in a while in a long sequence of trials. So that's where we would start to discuss kind of the unlikely idea. So I would put kind of unlikely here and here. So since it says it's very unlikely, this is where I would be encouraged to do the 0.001. It might occur once in a while in a long series of trials, but it's not going to happen very frequently. And then the last one, this outcome will occur more often than not. Okay, so it's not going to happen all the time, but it is going to happen pretty frequently. That's going to be the 0.6. 0.99 would be almost happening on every trial. So when we compare kind of 0.99 to 0.6, it's just happening more often than it's not happening. It's almost 50-50, but it's not almost every trial. So we have this range of impossible to certain with likely and unlikely in between. Our last example, it says a husband and wife decided to have children until they have at least one child of each sex, and the couple has 6 girls in a row. I believe that is like the McFall children there. Their doctor assures them that they are much more likely to have a boy next. Explain why the doctor is wrong. Okay, this is that myth of the law of averages. And so this is a myth. And actually, genetically, because they've had 6 girls in a row, it's more likely that they would continue to have 6 girls. But at the same time, if it is a 50-50 chance when the embryo is developed, it really could go one way or the other. So this is the law of averages, and it's a myth. The next child is still equally likely to be a boy or a girl. And so that's where, you can keep trying, but you probably can't fight genetics, and it could go either way. You'd have to be okay. The doctor shouldn't be saying that they're likely to have a boy next. It's still equally likely here. All right, so let me know if you have questions here, and have a good day.